So you've seen a couple of other examples, and so we're talking about, and let me turn my pen on, I apologize. We're talking about reactive material balances. And I'm kind of taking time to write that out. So before we worked on non-reactive material balances, and this time we're working on reactive material balances. And kind of a key characteristic of these problems are a balanced equation. And on the first section of this class, we had non-reactive material balances. And that dealt with, we can do a flow chart for this, but on this problem, the flow chart isn't quite as important. And but it is important in other contexts, so don't really forget it. But this, the balanced equation, is the key. And I can't get over that enough. And so we've seen, we have other videos where we went over the balancing equation process. We have another video where we talked about excess reactant, and hopefully that is familiar to you from chemistry that you've had in the past. And because I remember having it in the past. Hopefully you guys had it in the past as well, limiting an excess reactant. Right now I'm going to work on another reactive material balance problem, and I have it right here, and I'll bring it up to kind of this workout pane here. Oops, kind of fumbling around. Got to drag it. I might edit this out. I might not. My mistakes, but it's okay. All right, so this is one of my favorite problems. Tellurium is an element used in CMOS image sensors and solar cells. And if you are familiar with Telluride, Colorado, that telluride, I believe, is tellurium oxide. And it's mined there, I believe. I don't know where it used to be. I'm kind of throwing in useless trivia. Let me get back to the problem. Tellurium is an element used in CMOS image sensors and solar cells. A step in the tellurium refining process is to roast copper telluride, Cu2Te, which is also the logo for my boy band Too Cute, if you guys didn't know, and sulfuric acid. Ooh, that's an interesting process. So we're roasting copper telluride and sulfuric acid, and you have a chemical reaction that yields copper sulfate, tellurium dioxide, and sulfur dioxide, as well as water, H2O. And so we have kind of three. This is pretty standard for what's asked in these types of problems. Kind of three kind of sub-problems. So write a balanced equation for this process, and this is the key. This is the material balance. So the question that's the material balance is, if 100 kilograms of copper telluride is processed, what mass of sulfuric acid will you need? And what mass of tellurium dioxide will be produced from this process? So this is what we're trying to make, tellurium dioxide. So we will basically take this and refine it further later on in another processing step to make a solar panel or image sensor or something. This is probably a batch process, but we're going to draw it in terms of input and output just to be consistent with what we've had before. And so our input is going to be Cu copper telluride, which I actually think this is telluride, just referred to as telluride, and that's what Telluride, Colorado is named for. H2SO4, and our output's going to be SO2, H2O, and tellurium dioxide, which will then go to some other refining plant to be further refined into pure tellurium. So on the other problems we've had, we had mass flow rates or volume flow rates or molar flow rates or something like that, and you had to do some conversions, some unit conversions to figure out the output. Here we don't really have a mass flow rate, and this is kind of a batch process if you think about it, because we're roasting our copper telluride in H2SO4 in this tank, and or vat, whatever you want to call it, and we're kind of releasing SO2 water and tellurium dioxide, which is probably going to be recovered in a solid form. Again, the material balance is driven by the chemical equation. So let's start off by writing our chemical equation, or balancing our chemical equation. So that's actually the first question, write a balanced equation for this process. And so we've done this kind of before. And this is a little lengthy one. Oh, we're actually missing. I missed one here on my chart. Sorry about that. I missed the copper sulfate. So there's a lot of products here. I'll shrink it a little bit. And SO2 plus, plus, plus. And you've seen the other video hopefully by now. And so we have A, B on this side, and we can do X, Y, Z, W on this side. So it's a little bit longer than the other ones. So now we're going to do this by balances, basically. So it's input equals output. So that context is the same. And so for copper, and let me make it look more like a U. For copper, 2A is equal to X. So we don't have copper anywhere else here. For tellurium, A is equal to Y. We don't have tellurium anywhere else on the output. For hydrogen, we have 2B, and we only have hydrogen on the water here, equals 2Z. For sulfur, we have I'm pausing. We have it only once here. Sorry about my pause. We have one sulfur here, and we have another sulfur here. So SB equals X plus W. And for oxygen, oops, sorry about that. We have 4B This is a big one because there's oxygen everywhere. It's here, here, here. It's on every one. So it's on 4 of the outputs. 4b equals 4x. Hopefully you can write it on one sheet of paper, and hopefully you're following along. 4x plus 2y plus z plus 2w. Let me fix my z. All right, so some algebra, and we assume a basis. So basis is a is equal to 1. So if a is equal to 1, x is equal to 2. Here, a is equal to 1. That means y is equal to 1. This one, excuse me if you heard that. This one, b is equal to z, because the 2's cancel on both sides. And so we're going to have to come back and to this one. B equals x plus w. So we have an x so far. So b equals x plus w, so 2 plus w. And so we might want to stop there. 4b equals 4x plus 2y plus z plus 2w. So we have a lot of coefficients here, but we've solved for many. And we already know that b equals z here. And so we can kind of fix this. So we can rewrite this. We can substitute b for z. Oops, didn't switch back. X is 2, so 4 times 2 is 8. Y is 1 plus 2. Z equals b, and plus b, and then 2w. And let me see if I want to do another solve, another switcheroo. Yeah, we can write all this in terms of b, and then actually solve for b. So b equals 2 plus w. W equals plus b plus 2 times b minus 2. It's always these simple algebras that get me. 4b equals 8 plus 2 plus b plus 2b minus 4. All right. So let's move all the b's to one side. So minus b minus 2b is simply b equals 10 minus 4. B equals 6. All right, b equals 6. Now we can plug this 6 here. So w equals 6 minus 2. W equals 4. And now b equals z. B equals 6. Z equals 6. So we have a coefficient now for every variable. Alrighty. So I'm going to shrink it and I'll make it bigger to hopefully make everything easier for you all to see. And we have our friend now, a equals 1. So it's just simply b equals 6. x x2 y is 1, z is 6, w is 4. Woo! All right. So that's part A. We have our balanced equation. And man, I changed scales. I apologize. All right. All right. So now we have our balanced equation, which is the answer to part A. For part B, they want us to actually do something with this balanced equation. And they want to know what mass of sulfuric acid we're going to need. And I was saying this is pretty much the material balancing part, right? So we have 1,000 kilograms of copper telluride. What mass of sulfuric acid will you need? And then if you look ahead at part C, what mass of tellurium dioxide will you produce? Okay, so they're going to want to know how much tellurium dioxide we're making. And so the key players in these next two problems are going to be copper telluride, sulfuric acid, and tellurium dioxide. And we're given a mass. When we have a chemical equation, the ratios are really molar ratios. So here, I lost my 6. Sorry, I must have erased it by accident. 6H2SO4. And so the ratio of copper telluride to sulfuric acid here is 1 to 6. That's the molar ratio. So the given is 1,000 kilograms. Is the 1,000 kilograms of copper telluride. And we could actually have done this in terms of a rate, but we're kind of just looking at it in terms of using a balanced equation to solve this business. So we need the molecular masses to go back and forth between mass and moles. So we need molecular mass. And so for copper telluride, the molecular mass is 254.68. And I should probably check that. $254.78. According to Google. The molecular mass of sulfuric acid is, I looked this one up earlier, it's 98.08. And for tellurium dioxide, believe it was like 156 and change or something, 159.6. All right, so now we need to decide the units. And this is a recurring theme. So we're given 1,000 kilograms. I purposely didn't write this in with units because I want to decide the units. And so we're going to do this in kilograms per kilogram mole because we're in terms of kilogram. It's asking for mass. It didn't specify, so it's easier just to do it in terms of kilograms because you save yourself the conversion to grams. And so we can do this in one swift calculation. So given 1,000 kilograms, what mass, and let me do it in black just to match. So I'm kind of summarizing the problem down here, because up here it's asking, so if we have 1,000 kilograms of copper telluride, what mass of sulfuric acid will you need is what we're being asked. And so our basis now, 1,000 kilograms, and and so there are 254.78 kilograms in 1 kilogram mole. And so here's now where the chemical equation becomes our guide. There's a molar ratio, so we want to know how much H2SO4 we need. There's a 6-to-1 molar ratio. So we have 1 kilogram mole of copper telluride. This lets us set up how we're going to set up the rest of this calculation. And so we have a 1 kg, or kilogram mole, and the ratio is 1 to 6. 6 and so we want to get to mass of H2SO4, so we need our molecular mass of H2SO4. And so there's 98.08, what's the units? Kilograms of H2SO4 in 1 kilogram mole of H2SO4. I'm going to leave the calculation part up here, and I'll write the answer down here. I want to make sure it's big enough for you all to see it, especially if you're using a phone or something. So will our units cancel? Will we get what we want when we plug and chug in our calculator? Well, let's see. Let's cancel the units. So kilograms copper telluride cancels, kilograms copper telluride cancels, kilogram moles copper telluride cancels, and kilogram moles copper telluride. Okay, that cancels. I'm repeating myself, I apologize. This one cancels as well, so the kilogram moles H2SO4, and so we're left with kilograms of H2SO4, and that's what we want. We wanted to know what mass of H2SO4. So I'm going to plug and chug in my calculator here. 1,000 divided by 254.78 times 6 times 98.08. And I got, well, I should probably, maybe it doesn't matter. I was talking about the color of my pen. 2309.76. What are the units? Kilograms H2SO4. So this is the answer. Ooh, I apologize. I must have written something else over there one time. That's interesting. All right, so for C now, they want to know, let's go creep back up. They want to know what mass of tellurium dioxide will be produced from this process. So what mass of tellurium dioxide will be produced from this process? So again, chemical equation is the guide, and we can use our same basis of 1,000 kilograms of copper telluride. And so it's like an academic advice. You could use this as your basis, okay? But we already know that 1,000 is given. And so in case we made a mistake calculating our H2SO4, maybe it's smarter to use 1,000. I should have more faith in my calculation, so I could probably use H2SO4 as the basis as well. I'm going to go ahead and do it with 1,000 kilograms of copper telluride as the basis. And again, the molecular mass, 1 kilogram is 254.78 kilograms of copper telluride. And we have a ratio, I believe it's 1:1, but let's go back and look. So it's a 1:1 ratio, so 1:1. So there is 1 to 1 kilogram mole, and we asked for tellurium dioxide, right? TeO2. And 1 kilogram mole so 1 kilogram mole of TeO2 we said was 159.6 kilograms. And let's check and see if the units cancel. So kilograms copper telluride, kilograms copper telluride, kilogram moles copper telluride, kilogram moles copper telluride, kilogram moles tellurium oxide, kilogram moles tellurium oxide or tellurium dioxide, right? So let's plug this one in. I think we're going to get the answer we want, which is the mass of, wrote that in red because I forgot. 1,000 divided by 254.78, and there's nothing else really, times 159.6. And I got 626.42. And it's kilograms of tellurium dioxide. So we've done kind of a simple balance on a reactive material balance, our simple problem. Started off with a fairly lengthy balance actually to balance this equation, and I still love this algebraic way. If we're given things in terms of moles, there's another trick that I can show you later. However, this is a pretty good process to follow, and so always the steps we want to follow for this are 1, write a balanced equation. 2, I'm just going to say decide the units. And 3, calculate. And then be careful of conversions. And molar ratios, actually. And those are kind of 3 basic steps for solving reactive material balances. And if you have any questions, don't hesitate to email me.
Oh my. It's the end of the lecture. If you have any questions, you can email me at drobertson@utep.edu.